Okay, so let's now move on to the simulation. Already I've created a RBD packed object, the rigid body solver, and gravity. So nothing quite special yet. However, let's talk about the collision hole that we end up using for these pieces. Because once a piece becomes small enough, you don't want to use the convex hole option because it takes too much time to calculate that. Instead, and just to really show my point here, let's say that I say that I want everything to be a sphere, and I say show guide geometry. This loads super quickly because spheres are really fast to calculate. And also when this goes to sim, the spheres are going to calculate very quickly as well because it's a very simple object. But if I switch this over to convex hole, it's going to take a lot longer for this to think about everything. And when this goes to sim, it's going to increase our sim time pretty substantially as well. So what makes a lot more sense is to basically take a look at the piece scale on our points and say that if you are a bigger piece, then that is going to be a convex hole. And if you're a smaller piece, then go ahead and simplify that with a box or a sphere collision hole instead. That's going to improve the simulation time as well as what we see here in our viewport. So it's really pretty easy to do this. We have the copy to points right here, and we need to get rid of this p-scale right here because right now p-scale isn't being transferred over to our packed pieces. If we middle mouse, we don't see it there, and we get rid of this, and now we do. We have that going on. Let's also go ahead and use a RBD configure SOP. And on this RBD configure SOP, we need to specify this attribute only for the smaller pieces. So under the group right here, we can just use p-scale to find those pieces. And so if we go to the copy to points, be sure that p-scale isn't in this exclusion here. I believe by default, it should show up like that. So if you see that, then get rid of that. And if we middle mouse, we have p-scale. Now, be careful because on this copy to points, you're not going to be able to sort those values. If we go to the Geo spreadsheet and we try to sort these, it doesn't always do a good job. Of course, as I said that, it works, but trust me, sometimes this doesn't sort properly. And if that happens, then go to the RBD configure and try to sort down here instead. Anyway, what we're after here is about a middle value for these pieces. So if I just visually take this cursor down to about the middle, I can see that 0.022 is the middle. So I'll say, well, maybe let's actually include more pieces. So if you are p-scale less than 0.035, if that's you, then go to collision shapes, geo representation, and I want to turn you into a box. We could do a box, we could do a sphere. Spheres are going to not ever lie still on top of a surface. Boxes will. So that's why I'll do the box. On the assemble, we have the create name attributes. So we have our name. Now if we go to our DOF-nets, we should be able to see a combination of boxes and convex holes. And the cool thing about it is that we're only spending our simulation time and extra efforts on those big pieces which we can see. So this is just a really great optimization. This is going to speed up your sim time as well as your viewport and everything that you do. So I think this is an excellent step in the right direction. Before bringing in those collision objects, that'll slow everything down. Let's figure out velocity first. And so starting off, we'll go up to the scatter, turn down the number of points as we test things out. So there we go. We have maybe a bit more than that. Let's say 5,000. That's pretty good. And let's use a attribute randomize. We want a random velocity that exists within a 30-degree cone. So on here, we'll say attribute name, V for velocity. Distribution is going to be inside sphere. Cone angle of about 30. And I want that cone facing in the Y direction. So X, Y, Z. That will give us velocity vectors that are randomly situated within a 30-degree span. Let's actually change this to about 45, so we have a bit more randomization on that. And to see what those velocities are doing, let's use an add-sop, reduce this down to points, like so. And once we have those points, D for display, let's take our scale vectors here to 20, and we could turn on our velocity tails right there. And that'll give you an idea of where the velocity is currently pointing. So everything's going up right now. Again, that cone angle will show you exactly what it's doing when I go like that. And now let's actually add a bit more randomization to what we have here. These velocity vectors are going to be a good start, but what would be better is if we multiplied against them with a noise. So let's use a attribute noise on top of this. And we're going to start off with CD so that we can see what we're doing. And let's, again, set this up to the add. So there we go. There's our noise. Let's change this to zero-centered values as we preview the noise so that we can see what those colors are doing. And now I can adjust what we have. So taking the element size up, we'll go maybe right about there. Noise type, let's use a Manhattan F1. And then from here we could say positive values again, and we're going to multiply against V for velocity. If you want to add a bit more roughness, you can do that down here in the fractal and add a bit more roughness as well. What that does is it takes our velocity vectors and it varies them up a lot more. So to see what that did, if I go now to our amplitude and I turn that to 0, or if I turn that up, you can kind of see that it's just breaking up the length of those tails even more. And so it's creating these clumps of, general intensity, if you will. And that's a good thing. Okay, so once we have that, if we go to our simulation, go forward a few frames, nothing's going to happen right away because we need to go to the RBD packed object, say initial state, and inherit the velocity from point velocity. So we check that on, and then we also probably want to turn up that velocity. So for the attribute randomize, we're going to do this, set the global scale to about 5, and then on this noise, we'll also turn this up to probably about 3 or 5, something like that. Now that we have this, go forward a few frames, we should see it flying in random directions. It's kind of crazy right now, but we could see that now we have this. Pew! Like that. Okay, cool. Well, in the next video, let's talk about collision meshes. Let's blend this in with the overall motion of our original simulation, and we'll take it from there.